Welcome to The Sleepy Scientist. It's wonderful to have you here tonight. Before we begin, I'd love to know where in the world you're listening from. Let me know in the comments, I do love reading them. Maybe you're already tucked into bed, stretched out somewhere comfortable after a long day, or listening quietly while the rest of the world begins to slow down. Wherever you are, I hope you're warm, comfortable, and ready to let your mind wander for a while. If you'd rather listen with your screen off and your eyes closed, The Sleepy Scientist is also on Spotify. You'll find the link in the description so you can simply press play, set your phone aside, and drift off in the dark. And if you enjoy these calm journeys through science, a like and subscribe really does help this sleepy little channel keep going. If you're already subscribed, thank you for being here again. Tonight, we're following the life of a star all the way to one of the strangest endings nature can produce. We'll see how a massive star slowly runs out of ways to support itself, why some collapsing stars become neutron stars instead, and what finally has to happen before gravity wins completely and a black hole is born. It is admittedly quite a dramatic way for a star to end its life, but it happened a very long way away, a very long time ago, and tonight we can watch it unfold slowly, from a safe and comfortable distance. So get comfortable, let the day fade into the background, and let's begin. How does a star become a black hole? Look up at almost any dark patch of sky, and with enough patience or a good enough telescope, you will find stars scattered across it. Most appear as little more than points of light. Some are faint, some are bright, and a few may have been shining toward us since long before human beings began recording the night sky. Nothing about that distant glow immediately suggests a black hole. And yet, for some of the most massive stars, that quiet point of light is the beginning of exactly that story. A stellar black hole does not begin as something dark or mysterious. It begins as a star, governed by the same broad physical principles as every other star in the universe. Gravity pulls matter inward. Heat and pressure push outward. Nuclear reactions release energy deep inside the star. Particles jostle through the interior at extraordinary temperatures. Radiation works its way toward the surface. And for most of the star's life, these different effects settle into a remarkably stable balance. That balance is known as hydrostatic equilibrium. Gravity is always trying to compress the star. The material inside responds with pressure. In the hot interior, particles move rapidly and collide with one another. Radiation also contributes pressure, especially inside very massive stars. Most importantly, nuclear fusion continually releases energy in the core, helping maintain the temperatures required to keep that pressure high. A star, in other words, spends most of its life performing a very long balancing act. For stars like the Sun, that balance can continue for billions of years. Massive stars live rather differently. They possess much more material, which means gravity squeezes their interiors far more strongly. Their cores therefore become hotter and denser, and nuclear reactions proceed at a much greater rate. They have more fuel than a small star, but they burn through it so aggressively that they actually live for much less time. A star containing several times the mass of the Sun is already quite different from our own star. But when astronomers talk about the stars that undergo core collapse, they are usually interested in stars born with roughly 8 times the mass of the Sun or more. That figure is useful, but it needs to be handled carefully. A star beginning life with around 8 solar masses has entered a broad region where its central evolution can eventually become violent enough for the core to collapse. That does not mean an 8 solar mass star automatically produces a black hole. In fact, many stars that undergo core collapse leave behind neutron stars instead. And that distinction, is one of the most important parts of understanding how black holes are actually made. The popular version of the story can sound almost too simple. A very massive star runs out of fuel, gravity crushes it, and a black hole appears. The real process is much richer. A star can spend millions of years steadily transforming lighter elements into heavier ones. Eventually, if the star is massive enough, its core develops conditions that ordinary nuclear burning can no longer indefinitely support. The center collapses at enormous speed. Within less than a second, matter that had once occupied a region thousands of kilometers across can plunge inward toward dimensions measured in only tens of kilometers. Millions of years of stellar evolution can therefore lead to a decisive event lasting less time than a relaxed human heartbeat. But even then, a black hole is not guaranteed. The collapsing core may be halted temporarily by the extreme physics of neutron-rich matter. A neutron star may form, an outward shock may develop, a supernova may tear much of the original star apart and throw its outer layers into space, or the central object may continue gaining mass until even a neutron star can no longer support itself. That is where the black hole enters the story. It is helpful to separate several different meanings of mass, because they are often blurred together. There is the mass with which the star is born. Then there is the mass the star still possesses near the end of its life. Those two values can be very different. Massive stars can lose enormous quantities of material through powerful stellar winds, eruptions, or interactions with companion stars. Inside that changing star sits the core, whose mass and internal structure become especially important when collapse begins. And finally there is the compact remnant left behind after the event is over. A star might begin with many tens of times the Sun's mass, and yet produce a black hole weighing far less than that. Material may have escaped throughout the star's lifetime. More may be blasted away during the final collapse. Some may later fall back toward the center. This is why there is no perfectly clean rule saying that every star above one particular birth mass becomes a black hole, while every star below it becomes something else. Nature has not provided astronomers with quite such a convenient dividing line. Instead, the final outcome depends on how the star has evolved, how much mass it has lost, what its core looks like when collapse begins, and whether the enormous explosion mechanism that follows can remove enough material from the center. If the compact remnant remains within the range that neutron-rich matter can support, a neutron star survives. If too much mass remains concentrated in the center, or if additional material continues falling inward, gravity can push the remnant beyond that final stable state. Eventually, an event horizon forms. At that point, the object has become a black hole. So the transformation from star to black hole is not one sudden switch caused simply by being very massive. It is the final result of a long competition between nuclear physics, pressure, gravity, mass loss, stellar structure, and the extraordinary behavior of matter compressed far beyond anything encountered naturally on Earth. The darkness at the end begins with a star that for most of its existence looks perfectly ordinary from far away. It shines, it burns, and it quietly holds itself together. Until, eventually, it cannot. Mass is one of the simplest measurements we can make of a star, but it quietly controls almost everything about the life that star will lead. A star with more mass has stronger gravity. That stronger gravity squeezes its interior more tightly, raising the pressure and temperature at its center. Higher temperatures allow nuclear reactions to proceed more rapidly, and those reactions determine how quickly the star consumes its fuel, which elements it can eventually produce, and how long it can continue shining. So although a massive star begins with far more fuel than a smaller one, it does not necessarily live longer. Quite the opposite. A star several times heavier than the Sun can burn through its available nuclear fuel so quickly that its lifetime is measured in millions of years rather than billions. The most massive stars are therefore rather extravagant objects. They are born with enormous reserves of fuel and then proceed to spend them at a remarkable rate. Astronomers usually compare stellar masses with the mass of the Sun. One solar mass is roughly 2,000 billion kilograms. That is an almost comically large number by everyday standards, but using the Sun as a unit makes comparisons much easier. A star with 10 solar masses contains roughly 10 times the Sun's mass. A neutron star might contain around 1.5 solar masses. A stellar black hole might contain several, 10, 20, or many tens of solar masses. But there is an important complication. When astronomers talk about the mass of a star, they have to be careful about exactly when that mass is being measured. The zero-age main sequence mass is the mass a star possesses when it settles into the long, stable phase of hydrogen fusion that defines most of its life. This is effectively its starting mass as a mature star. The pre-collapse mass is what remains much later, shortly before the core gives way. Those two numbers can differ enormously. Massive stars lose material through powerful stellar winds. Some experience violent eruptions that throw large amounts of matter into space. If the star belongs to a binary system, a companion can strip material away or, in other circumstances, transfer additional material onto it. A star that began its life with 25 solar masses may therefore contain considerably less than 25 solar masses when its core finally collapses. This is one reason the usual mass thresholds are useful only as rough guides. Stars born with less than about 8 solar masses generally do not develop the massive iron-rich cores associated with ordinary iron core collapse. Their final evolution follows other routes, usually leaving behind white dwarfs. Above roughly 8 solar masses, core collapse becomes possible, and many such stars end their lives by producing neutron stars. As initial masses rise beyond roughly 20 solar masses, black hole formation becomes increasingly likely. But these figures do not form neat walls. A star born with 25 solar masses is not carrying a cosmic ticket that guarantees admission to black holehood. If it loses enough material, or develops a core whose structure allows a successful explosion to remove much of the surrounding matter, it can still leave behind a neutron star. Meanwhile, a star with a somewhat lower initial mass may develop an unusually compact core that is difficult for a supernova explosion to disrupt. More material can then remain near the center, increasing the chance that the remnant eventually becomes a black hole. What matters greatly during the final moments is not simply the star's original mass, but the structure hidden deep inside it. Astronomers and stellar physicists often distinguish between the helium core, the carbon and oxygen core, and the iron-rich core formed later in the star's evolution. Each represents material processed through different stages of nuclear burning. By the time collapse begins, the mass and density profile of these inner regions strongly influence what happens to the shock produced during the collapse. A compact, tightly bound core can be harder to explode. A less compact structure may allow the outgoing shock to escape more successfully and remove much of the star. This has led to an important idea known as islands of explodability. The name reflects the fact that the outcomes predicted by detailed computer models do not always change smoothly with increasing stellar mass. It would be convenient if every star below one mass produced a neutron star and every star above it produced a black hole. Actual stellar models are less cooperative. Successful explosions and failed explosions can appear in alternating ranges of initial mass. Two stars born with fairly similar masses can develop noticeably different internal structures because of the complicated sequence of nuclear burning stages near the ends of their lives. One may explode successfully, the other may collapse more completely. Chemical composition also matters, particularly something astronomers call metallicity. In astronomy, metallicity describes the abundance of elements heavier than hydrogen and helium. The term is rather generous. Oxygen, carbon, and many other elements that no chemist would call metals are happily included in the astronomical category. Stars with higher metallicity generally drive stronger stellar winds. Those winds remove mass throughout the star's life. Stars containing fewer heavy elements often lose less material and can therefore retain much more of their original mass until the final collapse. This is particularly important when considering stars that formed much earlier in cosmic history, when the universe contained fewer heavy elements than it does today. A low metallicity massive star can arrive at death with a heavier core and a larger surrounding envelope than a similar star forming in a metal-rich environment. Mass therefore remains the central influence on stellar fate, but it works through an entire lifetime of stellar evolution. The mass with which a star begins determines how strongly gravity squeezes it, how hot its interior becomes, how quickly it burns its fuel, and which nuclear reactions eventually become possible. But the star does not preserve its original condition all the way to death. It changes. It sheds material, builds heavier elements, grows different internal cores, and sometimes exchanges matter with a companion. By the time the final collapse begins, the question is no longer simply how massive the star once was. The more important question is what gravity has left to work with when the centre finally gives way. Deep inside a massive star, the conditions are so extreme that ordinary matter behaves very differently from anything we experience on Earth. The centre is compressed by the weight of everything above it. Temperatures climb into the millions of degrees, particles move at enormous speeds, and atomic nuclei are forced close enough together for nuclear fusion to occur. During the longest and most stable period of a massive star's life, hydrogen is the main fuel. Hydrogen nuclei combine to form helium, and in the process a small amount of mass is converted into energy. That energy slowly works its way outward through the star and eventually escapes from the surface as light and heat. At the same time, it helps maintain the pressure needed to resist gravity. This long-lasting state is known as the main sequence. For a star like the Sun, hydrogen fusion in the core is dominated by a sequence of reactions known as the proton-proton chain. In hotter and more massive stars, however, another process becomes increasingly important. This is the carbon-nitrogen-oxygen cycle. During the 1930s, physicist Hans Bethe helped explain how nuclear reactions could power stars and developed the detailed understanding of the carbon-nitrogen-oxygen cycle as one of the main mechanisms by which massive stars convert hydrogen into helium. Carbon, nitrogen, and oxygen nuclei participate in a sequence of reactions, effectively acting as intermediaries while hydrogen nuclei are transformed into helium. The carbon, nitrogen, and oxygen are not simply used up as ordinary fuel. They help make the reaction cycle possible. Because the rate of this cycle rises very steeply with temperature, it becomes especially efficient inside the hot cores of massive stars. And that creates one of the great ironies of stellar evolution. The more massive a star is, the more fuel it begins with. But the more massive it becomes, the stronger its gravity also becomes. That gravity compresses the core more intensely, increasing its temperature and dramatically accelerating the rate of nuclear fusion, so the most massive stars can burn through enormous quantities of hydrogen much faster than smaller stars. A star like the Sun can remain on the main sequence for roughly 10 billion years. A star with many times the Sun's mass may remain there for only a few million years. More fuel does not necessarily mean more time. In a massive star, it often means a much larger furnace. Eventually, the hydrogen in the central region becomes depleted. Fusion does not suddenly stop everywhere in the star. Instead, the core changes. The helium-rich center contracts under gravity, and that contraction raises its temperature. Hydrogen can continue fusing in a shell surrounding the core, while the outer layers of the star respond by expanding. Depending on the star's mass, composition, and mass loss history, it may become a red supergiant, swelling to hundreds or even more than 1,000 times the radius of the Sun. Other massive stars lose much of their outer hydrogen envelope through stellar winds or interactions with a companion. These stripped stars can remain much hotter and more compact at the surface. The appearance from outside may therefore be very different, even when the hidden core is following a broadly similar progression toward collapse. As the helium core grows hotter, helium fusion eventually becomes possible. Helium nuclei combine through reactions that produce carbon and oxygen. For a less massive star, this would already be approaching the end of the road. A sufficiently massive star can continue much further. Once helium in the center has been depleted, the core contracts again. Temperature rises again. Eventually carbon begins to burn. Later comes neon burning. Then oxygen. Then silicon. Each new stage requires more extreme conditions because heavier nuclei are more difficult to fuse. The core temperature climbs from tens of millions of degrees during earlier burning stages to billions of degrees during the final ones. And as the fuels become heavier, the time spent burning each one becomes dramatically shorter. Hydrogen burning can last for millions of years in a massive star. Helium burning may continue for hundreds of thousands of years. Carbon burning may last hundreds or thousands of years depending on the star. Neon burning can be reduced to a timescale of years. Oxygen burning may continue for months. Silicon burning can sometimes last only days. The star does not experience these changes as a tidy sequence in which the entire object switches from one fuel to another. Its interior becomes layered. Late in its life, a massive star can develop something resembling an onion. At the center lies material produced by the most advanced nuclear reactions. Around it sit shells in which different fuels are still burning. Silicon burning may occur deep inside, surrounded by oxygen burning, then neon and carbon burning farther out, with helium and hydrogen reactions continuing in more distant shells. Each layer produces different elements. The star becomes a nested chemical factory, with gravity continually compressing the center and nuclear reactions responding wherever temperature and density are high enough. This picture is useful, but real stellar interiors are more complicated than perfectly smooth onion layers. Convection can mix material. Burning shells can expand, contract, merge, or interact. Turbulent motion can alter the structure of the core. Small differences created during these final stages can later influence whether the star explodes successfully or collapses more completely. Another important process is quietly removing energy from the core during these late stages. Neutrinos are extraordinarily light, weakly interacting particles. They are produced in huge numbers inside very hot stellar interiors. Because neutrinos interact so weakly with ordinary matter, most can escape from the star far more easily than photons. A photon generated deep inside a star can spend an enormous length of time being repeatedly absorbed and scattered before its energy finally reaches the surface. A neutrino can simply pass through most of the star. During the advanced burning stages, neutrino production becomes so intense that it becomes one of the dominant ways the core loses energy. That loss matters. When neutrinos carry energy away, the core cools relative to what it would otherwise be. Gravity responds by compressing it further. Compression raises the temperature. Higher temperatures allow the next stage of nuclear burning to begin. So neutrino cooling helps accelerate the late evolution of the star. The final stages become a strange race in which the core repeatedly loses energy, contracts, heats up, and finds another fuel capable of sustaining it for a little longer. Meanwhile, the outer star may be changing just as dramatically. Massive stars can drive powerful stellar winds through radiation pressure. Over their lifetimes, these winds can remove a substantial fraction of the original stellar mass. Some stars undergo major eruptions and shed even larger amounts of material. Binary companions can strip away entire outer envelopes. A star that began life as an enormous hydrogen-rich object may therefore approach collapse as something much smaller and hotter, with much of its original material already scattered into space. This is why the visible surface does not tell the full story. The fate of the star is being decided much deeper inside. And every time gravity seems to gain the upper hand, nuclear fusion finds another temporary answer. Hydrogen becomes helium. Helium produces carbon and oxygen. Carbon, neon, oxygen, and silicon continue the process. Each stage buys the star more time. But each stage also creates heavier nuclei. Eventually, the star reaches a point where the next material produced no longer offers another useful source of fusion energy. The furnace has spent millions of years keeping gravity at bay. In doing so, it has slowly built the very core that will make that balance impossible to maintain. The long sequence of nuclear burning inside a massive star can continue only because each new fuel releases useful energy when its nuclei are rearranged. But there is a limit to how far that process can go. The reason comes down to something called nuclear binding energy. Atomic nuclei are held together by the strong nuclear force. Some nuclei are more tightly bound than others, which means the particles inside them sit in a lower energy state. When nuclear reactions move matter toward a more tightly bound arrangement, energy can be released. For light elements, this usually happens through fusion. Hydrogen nuclei can combine to form helium and release energy. Helium can participate in reactions that produce carbon and oxygen. In sufficiently massive stars, still heavier nuclei can be assembled through carbon burning, neon burning, oxygen burning, and silicon burning. Each stage pushes matter toward nuclei that are more tightly bound. At the other end of the nuclear landscape, very heavy nuclei can release energy by splitting apart. This is the basic principle behind nuclear fission. Between these two regions lies a group of nuclei around iron and nickel that are among the most tightly bound in nature. Once stellar matter reaches this region, the easy source of energy from fusion has essentially run out. The final advanced burning stage in a massive star is usually described as silicon burning, although the name hides a complicated network of nuclear reactions. At temperatures of several billion degrees, nuclei are continually broken apart and rebuilt. The result is not simply a core made of pure iron. Instead, the central region becomes dominated by iron group elements. One particularly important product is radioactive nickel-56. Nickel-56 later decays into cobalt-56, which in turn decays toward iron-56. These radioactive decays can become extremely important after a supernova explosion because the energy they release helps power the visible light from the expanding debris. But that later radioactive glow is not what causes the core to collapse. The immediate problem is more fundamental. Fusing iron group nuclei into still heavier nuclei generally requires an input of energy rather than providing the positive energy return that earlier fusion reactions supplied. The star has therefore reached the end of its ordinary sequence of useful fusion fuels. Gravity, unfortunately for the star, has not reached the end of anything. The iron-rich centre continues to grow because nuclear burning is still occurring in shells around it. Silicon burning outside the central core produces additional iron group material, which is gradually added to the region that can no longer generate enough new fusion energy to support itself in the familiar way. As more material accumulates, the central core moves closer to a critical mass. This mass is related to the Chandrasekhar mass, which is roughly 1.4 times the mass of the Sun for an idealized cold object supported by electron degeneracy pressure. The real core of a massive star is neither perfectly cold nor perfectly simple, so the precise point of instability varies. Its temperature matters. Its chemical composition matters. Rotation can alter the balance slightly. The number of electrons available per particle also matters. But the broad principle remains the same. There is only so much mass that electron degeneracy pressure can support. Electron degeneracy pressure is a quantum mechanical effect. Electrons obey the Pauli exclusion principle, which prevents identical electrons from all occupying exactly the same quantum state. As matter is compressed, electrons are forced into progressively higher momentum states, creating a pressure that can resist further compression. For a time, this pressure helps support the iron-rich core even after ordinary thermal support becomes increasingly inadequate. Then several processes begin to undermine it. One is photodisintegration. The central temperature becomes so high that photons carry enormous amounts of energy. Some of these energetic photons collide with iron group nuclei and break them apart into lighter components. This process consumes energy. Energy that might otherwise have helped maintain pressure is instead absorbed in dismantling nuclei that the star spent its final burning stages assembling. It is a remarkably unhelpful development from the star's point of view. Another process is electron capture. At sufficiently high density, electrons are pushed into atomic nuclei or interact with free protons. An electron and a proton can combine to produce a neutron and a neutrino. This has two important consequences. First, the process reduces the number of free electrons. Fewer electrons means weaker electron degeneracy pressure. Second, neutrinos carry energy away from the central region. The core is therefore losing pressure support at exactly the moment when gravity is becoming harder to resist. As density rises, electron capture becomes increasingly important. The core becomes more neutron-rich. Pressure falls. Gravity compresses the matter further. That further compression encourages still more electron capture. The balance that supported the center begins to unravel very quickly. Thermal pressure is no longer enough. Fusion can no longer provide a fresh energy source. Photodisintegration is consuming energy. Electron capture is removing pressure supporting electrons, and the mass of the core has grown large enough that electron degeneracy pressure can no longer hold the entire structure in equilibrium. The change from a stable stellar core to a collapsing one is therefore not simply a matter of the star running out of fuel in the ordinary sense. There may still be enormous amounts of nuclear material present. The problem is that the available reactions can no longer release energy in the way required to oppose gravity. the core has reached an energetic dead end. For millions of years, each contraction was followed by another stage of nuclear burning. Gravity squeezed the center, the temperature rose, a new fuel ignited, pressure increased again. The star found another temporary balance. Iron group nuclei break that rhythm. There is no ordinary next fuel that can rescue the core. Once the iron-rich center becomes sufficiently massive and the pressure supporting it begins to fail, the process accelerates dramatically. A structure that evolved gradually over millions of years is pushed out of equilibrium. The central matter starts moving inward. Density rises, electron capture intensifies, photodisintegration removes still more energy, and gravity finally gains an advantage that nuclear fusion cannot reverse. The furnace has reached the end of the periodic table that matters for energy-producing stellar fusion. What had been a slowly changing core is now about to become something entirely different. It is beginning to fall. One of the most important ideas in the entire story of stellar collapse begins not with gravity, but with quantum mechanics. As matter is squeezed to enormous density, a form of pressure appears that does not depend on heat in the usual sense. It is called electron degeneracy pressure, and it arises because electrons cannot simply be packed into identical quantum states without limit. The underlying rule is the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. Electrons belong to a class of particles known as fermions, and identical fermions cannot occupy exactly the same quantum state at the same time. That sounds abstract, but inside a dense stellar core it becomes something very physical. As gravity compresses matter, the available low-energy states for electrons begin to fill. New electrons are then forced into states with greater momentum. The result is a resistance to further compression. This pressure does not require the electrons to be extremely hot. It exists because of the structure of quantum mechanics itself. That is why a white dwarf can remain stable even after ordinary nuclear fusion has ended. It is also why the iron-rich core of a massive star can resist gravity for a time even when fusion is no longer supplying the same kind of support it once did. But electron degeneracy pressure has a limit. This was one of the great discoveries of 20th century astrophysics. During the 1930s, Subrahmanyan Chandrasekhar calculated what happens when a white dwarf becomes increasingly massive. A white dwarf is essentially the exposed compact core left behind by a lower mass star, supported largely by electron degeneracy pressure. At first, adding mass simply compresses the object more strongly. The electrons are pushed into higher momentum states, and the pressure rises. But eventually the electrons are moving so quickly that relativistic effects become important. Their speeds approach the speed of light. At that point, increasing their momentum no longer causes the pressure to rise quickly enough to keep pace with the growing strength of gravity. The support mechanism begins to lose the contest. Chandrasekhar found that there is therefore a maximum mass beyond which a cold, non-rotating white dwarf cannot remain stable through electron degeneracy pressure alone. That value is roughly 1.4 times the mass of the Sun. It is now known as the Chandrasekhar limit. The result was startling when it was first developed. At the time, the idea that a stellar remnant could become so massive that no stable white dwarf state was available raised an uncomfortable question. If electron pressure could not hold the object up, what happened next? The answer would eventually lead toward neutron stars and black holes. But the Chandrasekhar limit needs to be used carefully. It is not a universal number that applies in exactly the same way to every collapsing stellar core. The famous value of roughly 1.4 solar masses describes an idealized situation involving a cold white dwarf with a particular composition and structure. The core of a massive star shortly before collapse is much more complicated. It is hot. It contains a mixture of nuclei. Its electrons are being captured by protons and atomic nuclei. Its chemical composition is changing. Its entropy matters. Rotation can provide some additional support. The number of electrons available per unit mass also influences the result. So a real iron-rich stellar core does not simply sit quietly at 1.39 solar masses and then collapse the instant another convenient fraction of matter arrives. Nature is rarely that tidy. Instead, the effective instability mass depends on the physical state of the core. Still, the Chandrasekhar limit captures the central idea extremely well. There is only so much mass that electron degeneracy pressure can support. Once the core moves beyond that supportable range, equilibrium is lost. It is also important to understand what this limit is not. The Chandrasekhar limit is not the minimum mass required to make a black hole. It is not a black hole threshold. And it is not a rule applied to the total mass of the original star. A massive star can contain 10, 20 or many more solar masses in total, while its central iron-rich core contains something of order 1.5 solar masses. The surrounding material may still extend outward for millions or even hundreds of millions of kilometers. The instability begins in the core. The rest of the star does not need to be compressed anywhere near as strongly at that moment. The central region is what first crosses the important threshold. And even then, crossing this first mass barrier does not mean that a black hole has already formed. It means only that the current form of support has failed. Electron degeneracy pressure can no longer maintain the core as it was. Gravity begins driving the matter inward much more rapidly. As density rises, electrons are forced increasingly close to protons. Electron capture becomes more common. Electrons and protons combine to form neutrons and neutrinos. The number of free electrons falls, weakening electron degeneracy pressure even further. This creates a powerful feedback. Compression encourages electron capture. Electron capture reduces electron pressure. Reduced pressure allows still more compression. The core is no longer gently adjusting itself. It is entering dynamical collapse. Matter begins moving inward on a timescale comparable to the freefall time of the core, measured in fractions of a second rather than thousands or millions of years. The densities climb toward values associated with atomic nuclei. Protons and electrons can no longer remain arranged in anything resembling ordinary atoms. The character of the matter itself begins to change. This is why the Chandrasekhar limit is best thought of as the first major mass barrier in the path toward a black hole. Crossing it removes the possibility of a stable electron-supported core. But another form of support may still appear. At still greater density, neutron-rich matter can resist compression through neutron degeneracy pressure and the strong nuclear force. If the collapsed remnant is light enough, that new form of support may halt the collapse and leave behind a neutron star. If the remnant eventually becomes too massive even for that, then gravity faces one final barrier. And unlike the first one, crossing that later threshold can lead directly to the formation of a black hole. The strange part is that the first decisive step toward such an extreme object is governed by something almost invisible, a quantum rule about which states electrons are allowed to occupy. For most of the star's life, gravity battled heat and nuclear pressure. Near the end, it begins battling quantum mechanics itself. Once the iron-rich core loses the ability to support itself, the pace of events changes almost beyond recognition. For millions of years, the star evolved through comparatively gradual adjustments. Nuclear fuel was consumed, new burning stages began, and the core slowly became hotter and denser. But when the balance finally fails, stellar evolution gives way to dynamical collapse. The core begins to fall inward under its own gravity. What had once taken centuries, years, or days to change can now transform in a fraction of a second. Before collapse, the central iron-rich region may be thousands of kilometers across. As gravity takes control, that enormous volume contracts toward dimensions measured in only a few tens of kilometers. The motion is extraordinarily fast. Material deep inside the star accelerates inward to a substantial fraction of the speed of light. But the entire core does not collapse as one perfectly rigid object. Different regions behave differently. The innermost part initially contracts in an approximately coordinated way, with material at different radii moving inward while broadly preserving the shape of the central density profile. Physicists describe this as homologous collapse. Farther out, the situation becomes much more violent. The outer part of the core falls inward supersonically. Matter there is moving faster than pressure disturbances can travel through the material, which means different regions cannot smoothly communicate changes to one another as the collapse proceeds. Inside this rapidly contracting environment, electron capture becomes increasingly important. Electrons are squeezed into protons, producing neutrons and electron neutrinos. The basic reaction converts one proton and one electron into a neutron while releasing an electron neutrino. This process has a profound effect on the collapsing material. The number of free electrons decreases, which weakens the electron degeneracy pressure that had previously helped resist gravity. At the same time, the core becomes progressively richer in neutrons. The importance of neutrons in compact stars became physically meaningful only after James Chadwick discovered the neutron in 1932. Before that discovery, astronomers and physicists did not yet possess the particle needed to understand how stellar matter could be compressed beyond the electron-supported state of a white dwarf. Once neutrons were known to exist, an entirely new possibility became available. Matter might be compressed until electrons and protons were effectively transformed into neutron-rich material. That is precisely the direction the collapsing core now takes. At first, many of the neutrinos created by electron capture escape relatively easily. Neutrinos interact only weakly with matter, so under ordinary conditions they can pass through enormous amounts of material almost as though nothing were there. But the collapsing core is rapidly becoming anything but ordinary. As density climbs, even neutrinos begin to encounter enough matter that their journey outward becomes difficult. Eventually the central region becomes effectively opaque to them. The neutrinos are trapped. Instead of immediately escaping, they scatter repeatedly through the extraordinarily dense material and become temporarily locked into the collapsing core. Meanwhile, another process is draining energy. At temperatures of billions of degrees, energetic photons collide with iron group nuclei and break them apart. This is photodisintegration. Heavy nuclei can be dismantled into helium nuclei, neutrons and protons. Breaking them apart requires energy. So rather than helping support the star, some of the thermal energy in the core is being consumed by the destruction of nuclei that earlier fusion stages worked so hard to create. Gravity is therefore being helped from several directions at once. Electron capture reduces pressure. Neutrinos remove or redistribute energy. Photodisintegration consumes energy. And the core continues falling inward. The density rises at an astonishing rate. Eventually it approaches nuclear density, the characteristic density found inside atomic nuclei. This is roughly a few 100 million billion kilograms in every cubic meter. Numbers like that are difficult to picture. A useful comparison is to imagine something with the mass of a large mountain compressed into a volume much smaller than a grain of sand. That begins to suggest the kind of matter involved. At these densities, the familiar separation between individual atomic nuclei has essentially disappeared. The material has been compressed so strongly that nuclear physics begins to dominate the behavior of the entire central object. Gravity is also entering a regime where Albert Einstein's general theory of relativity becomes increasingly important. In ordinary stars, Newtonian gravity provides an excellent approximation for many purposes, but as a large amount of mass is compressed into a region only tens of kilometers across, space-time curvature becomes strong enough that a fully relativistic description is needed. Gravity is no longer adequately described as a simple force acting through an otherwise fixed background. The geometry of space-time itself becomes part of the problem. Even so, reaching this extreme state does not mean a black hole has already formed. That distinction is essential. Core collapse and black hole formation are not the same event. As the inner core approaches nuclear density, the behavior of matter changes dramatically. Neutron degeneracy pressure becomes important, and the strong nuclear force produces additional resistance to further compression. The collapsing inner core can suddenly stiffen. Its inward motion can be slowed sharply. For a brief moment, gravity encounters a new obstacle. The material that electron degeneracy pressure could no longer support has been compressed into a completely different state, one in which neutron-rich matter may be able to resist further collapse. A proto-neutron star can begin to form. It is extraordinarily hot, extremely dense, and still surrounded by material rushing inward from the rest of the star. Whether it survives is another question entirely. For now, the collapse has taken a stellar core thousands of kilometers wide and crushed it toward the dimensions of a city in less than a second. The star has crossed into a regime where quantum mechanics, nuclear physics, neutrinos and general relativity all become important at once. Gravity has not yet necessarily created a black hole, but it has transformed the center of the star beyond recognition. As the collapsing core approaches nuclear density, something remarkable happens. For a fraction of a second, gravity appears to meet serious resistance. The matter in the center has been compressed so violently that the usual picture of separate atomic nuclei has broken down. Neutrons are packed extraordinarily close together. Neutron degeneracy pressure becomes important, and the short-range behavior of the strong nuclear force begins to oppose further compression. The inner core suddenly becomes much stiffer. Its collapse slows sharply. This does not mean the star has returned to anything resembling its earlier stability. The object forming at the center is enormously hot, still evolving, and surrounded by layers of matter continuing to fall inward. It is known as a proto-neutron star. A proto-neutron star is not yet an ordinary mature neutron star. It contains trapped neutrinos, large numbers of electrons and other leptons, and temperatures reaching tens of billions of degrees. Its structure will change dramatically as it cools, loses neutrinos, and possibly gains additional matter. For the moment, however, it provides the first serious barrier against the collapse. When the innermost core is abruptly decelerated, the change produces what is commonly called core bounce. The term can sound as though the entire central object simply rebounds like a ball hitting the floor. The actual process is more subtle. The inner region stiffens and slows so suddenly that a pressure wave begins moving outward into material that is still rushing inward. As this wave travels into the outer part of the collapsing core, it steepens into a shock. For a brief moment, this looks like the beginning of the supernova explosion. An outward moving shock has formed deep inside the star, and enormous amounts of energy have been released. It would be tempting to imagine that the problem is now solved. Unfortunately for the star, the shock immediately encounters some rather expensive obstacles. One of them is the heavy nuclei in the infalling material. The shock heats these nuclei intensely and breaks many of them apart into lighter particles, including neutrons and protons. This process requires energy. The shock, therefore, spends a significant part of its energy dismantling nuclei as it tries to move outward. Neutrinos also carry energy away from the region. The result is that the shock rapidly loses strength. Instead of racing all the way through the star, it typically stalls within a few hundred kilometers of the center. The young proto-neutron star remains buried underneath it, while fresh material continues falling through the stalled shock and onto the central object. At first glance, this seems like a failure, but the collapse has released an extraordinary reservoir of energy. The gravitational binding energy liberated as the core shrinks into something only tens of kilometers across is of order 10,000 billion joules. Almost all of that energy does not appear as visible light. Roughly 99% eventually escapes in the form of neutrinos. This makes neutrinos one of the most important parts of the entire event. The core collapse itself occurs in less than a second, but the proto-neutron star continues releasing neutrinos for several seconds as it cools and contracts. Because neutrinos emerge from regions much deeper than ordinary light can escape from, they carry information about the hidden central engine of the collapse. Astronomers received an extraordinary demonstration of this in 1987. A massive star exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The event became known as supernova 1987A. Shortly before the visible supernova light reached its maximum brightness, underground detectors recorded a small burst of neutrinos. Kamiokande 2 in Japan detected neutrinos from the event. The Irvine, Michigan Brookhaven detector in the United States also recorded them. The Baksan Neutrino Observatory in the Soviet Union detected additional events. Only a few dozen neutrinos were recorded in total across the detectors, yet their importance was enormous. They provided direct evidence that a collapsing stellar core releases vast amounts of energy through neutrinos, just as theoretical models predicted. Masatoshi Koshiba played a central role in the Kamiokande experiment, and later received part of the Nobel Prize in Physics for pioneering contributions to neutrino astrophysics. Supernova 1987A remains one of the clearest observational windows humanity has ever had into the hidden collapse of a massive stellar core. The neutrinos do more than escape. Some interact with the material sitting just behind the stalled shock. A small fraction of their enormous energy can be deposited there. This process is known as neutrino heating. Even though only a tiny proportion of the total neutrino energy is absorbed, the total reservoir is so large that this small fraction may be enough to help revive the shock. The material behind the shock is also far from calm. Hotter regions rise, cooler material falls, convection develops, turbulence churns through the gas. The stalled shock itself can begin to move unevenly, sometimes sloshing from side to side or developing large-scale spiral motions. One important phenomenon is known as the standing accretion shock instability. This instability can distort the stalled shock and help create conditions in which neutrino heating becomes more effective. The exact combination of neutrino heating, convection, turbulence, and shock instability remains an active area of research, because the physics is highly complicated and strongly three-dimensional. The fate of the star is still undecided. If the shock is successfully revived, it may begin moving outward again and produce a supernova explosion. The proto-neutron star may then remain behind as a stable neutron star. But that is only one possibility. If the explosion is weak, some ejected material can later fall back toward the center and add enough mass to turn the neutron star into a black hole. If the shock never recovers strongly enough, matter may continue pouring onto the proto-neutron star until it exceeds the maximum mass that neutron-rich matter can support. In that case, black hole formation can occur very quickly. So the few seconds after core bounce contains several possible endings. A neutron star may survive. A supernova may succeed, but still leave a black hole later. Or the central object may collapse again before the explosion ever truly escapes. The star has reached a point where tiny differences in how energy and matter move through the collapsing core can determine whether anything solid remains at the center at all. The shock created during core bounce does not simply race outward and tear the star apart. In fact, one of the great challenges in understanding supernovae is explaining how that stalled shock manages to become an explosion at all. For a short time after the core collapses, the shock sits only a few hundred kilometers from the center, while matter from the outer core continues to fall inward through it. That incoming material carries enormous momentum. The shock is therefore trying to move outward, while fresh matter is still raining down from above. At the same time, the shock must work against the gravitational pull of the compact object forming at the center and the weight of the stellar layers farther out. It is not an especially favorable situation. One of the leading explanations for how the shock can recover is known as the delayed neutrino-driven explosion mechanism. The basic idea was developed through work by researchers including James Wilson and Hans Bethe. The proto-neutron star releases an immense stream of neutrinos as it cools. Most of those neutrinos pass outward without interacting very much at all. But not all of them. A small fraction deposit energy into the material just behind the stalled shock. That may sound inefficient, and it is. The useful fraction is tiny compared with the total neutrino output. But the total neutrino energy is so enormous that even a small percentage can matter. The heated material behind the shock becomes more buoyant. Hotter regions rise. Cooler material falls back toward the center. This produces convection. Instead of the region behaving like a perfectly neat collection of spherical shells, it begins to churn. That motion is important because material that remains in the heating region for longer has more time to absorb energy from neutrinos. Turbulence, therefore, helps the star make better use of a limited energy supply. The shock itself can also become unstable. One important effect is the standing accretion shock instability. Rather than remaining as a perfectly spherical shell, the stalled shock can begin to slosh from one side to another. In some cases, it can develop large spiral motions. These distortions redistribute energy and momentum through the collapsing material. They can also increase the time some gas spends in the region where neutrino heating is strongest. Taken together, neutrino heating, convection, turbulence, and shock instability can gradually push the system toward a tipping point. If enough energy accumulates behind the shock, its outward motion can begin again. Once that happens, the balance can change rapidly. The shock expands, the pressure behind it rises. Infalling material has farther to travel before reaching the center. More of the star begins moving outward instead of inward. A supernova explosion can finally develop. Understanding this process has required increasingly sophisticated computer simulations. Early models often assumed perfect spherical symmetry. That makes the mathematics far easier. But a real collapsing star is not perfectly spherical. It contains turbulent flows. It may be rotating. Magnetic fields may be present. Its nuclear burning shells can already be uneven before collapse begins. The shock can wobble, stretch, deform, and break symmetry. Modern simulations therefore model the collapse in 2 and 3 dimensions. These calculations are extremely demanding because they must combine gravity, nuclear physics, neutrino transport, fluid motion, and sometimes general relativity over vastly different scales. Even with modern supercomputers, accurately reproducing every part of a core collapse remains difficult. But the broad picture has become much clearer. A typical core collapse supernova carries kinetic energy of around 100 billion joules in its expanding ejecta. That is an extraordinary amount of energy. Yet it is still only a small fraction of the total energy released by the collapse. Most of that larger energy budget leaves in neutrinos. The visible explosion is almost the smaller side effect of a much deeper gravitational event. As the shock moves outward, it begins ejecting the stellar mantle and, if present, much of the outer envelope. Material that spent millions of years being processed inside the star is thrown into interstellar space. Oxygen, silicon, calcium, iron group elements, and many other nuclei are carried outward. Some of those elements may eventually become part of new stars, planets, or clouds of gas. The supernova therefore destroys one star, while helping enrich the material from which future systems can form. The bright light seen from far away is not produced simply because the shock remains luminous forever. Radioactive material also plays an important role. Nickel-56 produced during the explosion decays into cobalt-56. Cobalt-56 then decays toward iron-56. These radioactive decays release energy that heats the expanding ejecta. That energy helps power much of the visible supernova light curve after the initial explosion. So the mechanism that launches the explosion and the mechanism that keeps it bright are related but not identical. The shock is revived by conditions near the collapsed core. The later glow is strongly influenced by radioactive decay in the expanding debris. Real supernovae are also rarely perfectly symmetrical. One side can receive more energy than another. Material can be ejected unevenly. That asymmetry can give the compact remnant a recoil. Neutron stars are sometimes born with what astronomers call natal kicks, sending them through space at hundreds of kilometers per second. Some black holes may also receive kicks, although the details depend strongly on how much material is ejected and how the black hole forms. An important point is that seeing a successful supernova does not guarantee that the final remnant will remain a neutron star. The central object may continue gaining mass even after the shock begins moving outward. Some material may still fall inward. Other material may initially be ejected, but later fail to escape completely. If enough of it returns, the compact remnant can become too massive to remain stable. A black hole can then form after the supernova has already taken place. The dividing question is therefore not simply whether the star explodes, it is whether the explosion removes enough material from the centre. If enough mass escapes, the remnant may settle as a neutron star. If too much matter remains bound, or continues to fall inward, gravity is given another opportunity. The explosion may win the first contest, gravity may still win the last one. A collapsing stellar core does not always become a black hole. If the central remnant remains within the range that extremely dense nuclear matter can support, gravity can be halted once again. The result is a neutron star, one of the most compact objects known that still possesses a physical surface. The basic idea is similar to the earlier role played by electron degeneracy pressure, but the conditions are far more extreme. During collapse, electrons are increasingly captured by protons, producing neutrons and neutrinos. By the time the central matter reaches roughly nuclear density, the star has been compressed into material dominated by neutrons. At these densities, neutron degeneracy pressure becomes important. Neutrons, like electrons, obey the Pauli exclusion principle. Identical neutrons cannot all occupy the same quantum states, so forcing enormous numbers of them into a tiny volume generates resistance to further compression. But a neutron star is not supported by neutron degeneracy pressure alone. The strong nuclear interaction between particles also contributes substantially. At very short distances, the behavior of nuclear matter becomes strongly resistant to additional compression. Together, quantum statistics and nuclear interactions can establish a new equilibrium against gravity. If the remnant is not too massive, the collapse stops. What remains is astonishingly small. A typical neutron star contains around 1.4 times the mass of the Sun. Observed neutron star masses span a broader range, from a little above 1 solar mass to beyond 2 solar masses. All of that matter is compressed into an object only around 20 to 28 kilometers across. A neutron star could therefore fit comfortably inside the boundaries of a large city while containing more mass than the Sun. Its average density is comparable to the density of an atomic nucleus. A piece of neutron star matter only the size of a sugar cube, if it could somehow exist under ordinary conditions, would have a mass of roughly hundreds of millions or even billions of tons. The comparison is useful, although such matter could not simply be removed and placed on a table. Without the immense gravity and pressure of the neutron star, it would not remain in the same state. The interior is also much more complicated than the common description of a neutron star as one enormous atomic nucleus. Near the surface lies a solid crust. The outer crust contains atomic nuclei arranged in a lattice surrounded by highly mobile electrons. Deeper down, increasing pressure forces the nuclei to become progressively more neutron-rich. Eventually, neutrons begin escaping from the nuclei, producing an inner crust containing nuclei, electrons, and a sea of free neutrons. Many of those neutrons are expected to behave as a superfluid. A superfluid can move with effectively no ordinary viscosity, producing behavior very different from familiar liquids. Deeper still lies the outer core, where the matter is thought to consist mainly of neutrons along with smaller numbers of protons, electrons, and other particles. The innermost regions are much less certain. The density there may reach several times that found inside ordinary atomic nuclei. Under such conditions, matter may take forms that cannot yet be reproduced directly in laboratories. The center might contain unusual arrangements of neutrons and protons, additional particles, or perhaps states in which the quarks normally confined within protons and neutrons behave differently. Exactly what exists there depends on the equation of state of ultra-dense matter, which remains one of the major open problems in modern nuclear astrophysics. The idea that supernovae could create neutron stars appeared remarkably soon after the neutron itself was discovered. During the 1930s, Walter Baade and Fritz Zwicky proposed that supernova explosions could represent the transformation of ordinary stars into neutron stars. At the time, this was an extraordinarily bold suggestion. Decades later, observations provided compelling evidence that such objects really existed. In 1967, Jocelyn Bell Burnell, then a graduate student working with Anthony Hewish, noticed a remarkably regular pulsating radio signal. The source produced pulses with such precise timing that its nature was initially mysterious. More pulsating sources were soon found. These objects became known as pulsars. The interpretation that emerged was that pulsars are rapidly rotating neutron stars with intense magnetic fields. Thomas Gold was among the scientists who strongly developed the rotating neutron star explanation. Radiation is emitted from regions associated with the magnetic poles. Because the magnetic axis is usually tilted relative to the star's rotation axis, the radiation beams sweep through space as the neutron star spins. If one of those beams repeatedly crosses Earth, astronomers detect a sequence of pulses. The effect is often compared with the rotating beam of a lighthouse. Some neutron stars rotate slowly, perhaps once every several seconds. Others spin much faster. Millisecond pulsars can rotate hundreds of times every second. That speed becomes easier to understand when the enormous contraction involved in stellar collapse is considered. The original stellar core possessed angular momentum while extending across thousands of kilometers. When that material is compressed into an object only a few tens of kilometers across, conservation of angular momentum can dramatically increase the rotation rate. It is similar in principle to an ice skater spinning faster after pulling their arms inward, although the neutron star version is rather more committed to the idea. Neutron stars can also possess extraordinary magnetic fields. A particularly extreme class is known as magnetars. Their surface magnetic fields can be hundreds or thousands of times stronger than those of ordinary pulsars and trillions of times stronger than Earth's magnetic field. These intense fields can produce powerful bursts of high-energy radiation and dramatic activity in the neutron star's crust and magnetosphere. Despite all of these exotic properties, one distinction matters especially when comparing a neutron star with a black hole. A neutron star has a material surface. Matter falling toward it eventually encounters the crust. The infalling material can be heated to enormous temperatures and release radiation when it strikes the surface. A black hole is different. It has no material surface waiting underneath the infalling gas. Instead, it possesses an event horizon, a boundary beyond which outward escape is no longer possible. This makes the neutron star a genuine alternative final state rather than merely an unfinished black hole. If its mass remains low enough, it can persist for immense periods of time. But its survival is conditional. A neutron star in a binary system may gradually collect material from a companion. Two neutron stars may eventually merge. A newly formed neutron star may continue receiving matter that failed to escape during the supernova. If enough additional mass accumulates, the balance can be lost. The same object that once resisted gravity successfully can cross its final stability limit. And when even neutron-rich matter can no longer support the weight above it. There is no known stronger stable stellar state waiting to take over. The neutron star can collapse again. This time, the destination can be a black hole. A neutron star can resist gravity only up to a point. That point is the second great mass barrier in the life of a collapsing star. The first was reached when electron degeneracy pressure could no longer support the stellar core. Crossing that boundary forced the core to collapse into a much denser state. Neutrons, the strong nuclear force, and the quantum rules governing fermions then provided a new source of pressure. For a while that can be enough, but neutron-rich matter does not possess unlimited strength. If too much mass is concentrated into a neutron star, gravity eventually becomes stronger than every form of pressure available inside it. Understanding where that final boundary lies requires both nuclear physics and Albert Einstein's general theory of relativity. In 1939, Richard Tolman, Julius Robert Oppenheimer, and George Volkoff developed the relativistic description of how an extremely compact spherical star can remain in hydrostatic equilibrium. Their work led to what is now generally called the Tolman-Oppenheimer-Volkoff limit. In broad terms, this is the maximum mass that a cold, non-rotating neutron star can support before gravitational collapse becomes unavoidable. It sounds similar to the Chandrasekhar limit for white dwarfs. But there is an important difference. The Chandrasekhar limit can be estimated quite cleanly because the physics of electron degeneracy pressure is comparatively well understood. The maximum neutron star mass is more uncertain because the behavior of matter at several times nuclear density is still not known precisely. The problem centers on something called the equation of state. An equation of state describes how matter responds to compression. It connects quantities such as pressure, density, temperature, and composition. For ordinary gases, liquids, and solids, equations of state can often be measured directly in laboratories. For the center of a neutron star, that is impossible. The pressures and densities are simply too extreme. The inner core of a neutron star may contain matter compressed to several times the density found inside an atomic nucleus. No laboratory on Earth can create a stable sample of matter under those conditions and simply leave it sitting around long enough to measure its properties. Physicists therefore have to combine nuclear theory, particle physics, astronomical observations, and computer modeling. Different possible equations of state predict different neutron star structures. Some describe relatively stiff matter. In this context, stiff means that pressure rises strongly as density increases. A stiff equation of state can support a heavier neutron star. A softer equation of state provides less pressure at the same density and generally produces a lower maximum mass. Observations have already placed an important lower boundary on the answer. Astronomers have measured several neutron stars with masses close to or slightly above 2 solar masses. That means any realistic model of neutron star matter must be capable of supporting at least about twice the mass of the Sun. If a proposed equation of state predicts that neutron stars should collapse at only 1.6 solar masses, for example, then observations of 2 solar mass neutron stars immediately rule it out. The exact upper limit remains uncertain. Current theoretical and observational work generally places the maximum mass of a cold, non-rotating neutron star somewhere in the broad region between about 2 and 3 solar masses. The true value is likely to be narrower than that, but it has not yet been measured directly with complete confidence. And even that description contains several hidden complications. One of them is rotation. A rapidly spinning neutron star can support more mass than an otherwise identical non-rotating one. Rotation produces an outward centrifugal effect that partly opposes gravity. The faster the star spins, the more additional support it can receive. This can create what is known as a supramassive neutron star. Such an object may contain too much mass to survive if it were not rotating so rapidly. For a time, its spin keeps it stable. But neutron stars gradually lose rotational energy. Magnetic fields can carry energy away. Radiation can remove angular momentum. Interactions with surrounding matter may alter the rotation. As the star slows, the extra support becomes weaker. Eventually, the object may cross its stability boundary. Nothing needs to add more matter. The neutron star can collapse simply because the rotation that was keeping it alive is no longer sufficient. A newborn proto-neutron star introduces another complication. Immediately after core collapse, the object is extraordinarily hot. It also contains trapped neutrinos, those conditions influence the pressure inside it. A hot, lepton-rich proto-neutron star can therefore support a somewhat different amount of mass from the colder neutron star it may eventually become. Over the following seconds and minutes, neutrinos escape and carry energy away. The object cools. Its internal composition changes. Its pressure profile changes with it. A proto-neutron star that was initially stable can therefore become unstable later. This creates another route to delayed black hole formation. The distinction between baryonic mass and gravitational mass is also important. Baryonic mass refers roughly to the combined rest mass of the particles making up the object, particularly its protons and neutrons before gravitational binding is taken into account. Gravitational mass is the mass inferred from the object's gravitational influence on its surroundings. The two are not identical. When a stellar core collapses, a tremendous amount of energy is released. Much of that energy leaves as neutrinos. The neutron star is also held together by an enormous amount of gravitational binding energy. Because energy contributes to mass, losing that energy reduces the gravitational mass of the final object. A neutron star may therefore contain a baryonic mass noticeably greater than the gravitational mass an astronomer would measure from its orbit. The difference can amount to a substantial fraction of the Sun's mass. All of this means that a newly collapsed stellar core can follow several paths. One possibility is straightforward. Its final mass remains comfortably below the maximum stable neutron star mass. It cools, loses neutrinos, and survives. Another possibility is continued accretion. Material from the surrounding star may continue falling onto the proto-neutron star after the initial collapse. Every additional piece of matter increases the gravitational burden. If enough accumulates, the object crosses the maximum mass and collapses into a black hole. A third possibility involves temporary support. The object may initially survive because it is hot, rapidly rotating, or both. As it cools or spins down, that additional support disappears. The same amount of matter that was stable moments, minutes, or perhaps much longer earlier may become unstable. The neutron star then collapses without needing a dramatic new external event. There is also an intriguing observational question surrounding the masses of compact objects. For many years, astronomers noticed an apparent gap between the heaviest known neutron stars and the lightest clearly identified black holes. Neutron stars were commonly found below a little more than 2 solar masses, while many stellar black holes appeared above roughly 5 solar masses. This suggested a possible lower mass gap, but the boundary has become less tidy as observations have improved. Gravitational wave detections have revealed compact objects with masses in the uncertain region between obvious neutron stars and obvious black holes. Some may be unusually heavy neutron stars. Others may be unusually light black holes. In certain cases, the observations do not yet allow astronomers to determine which type of object was present. That ambiguity is scientifically useful. Each new measurement helps narrow the possible maximum mass of neutron stars and tests theories describing matter at extreme density. Eventually, the physics comes down to a simple but profound condition. A stable star requires some form of pressure capable of balancing gravity. For ordinary stars, thermal pressure and radiation help provide that support. For white dwarfs, electron degeneracy pressure can dominate. For neutron stars, neutron degeneracy, nuclear interactions, and the detailed behavior of ultra-dense matter provide the final known resistance. But every one of these mechanisms has limits. Once the mass becomes too large for any stable pressure profile to exist, the object cannot simply become a slightly denser neutron star and carry on. Within general relativity, there is no known stable stellar configuration beyond that point. Gravity continues compressing the matter. The radius shrinks. Space-time curvature becomes more extreme, and once the collapse carries enough mass inside the critical region from which light itself can no longer escape, an event horizon forms. The neutron star has crossed its final mass barrier. It has become a black hole. A supernova explosion does not always make a clean separation between the material that escapes and the compact object left behind. Some of the stellar debris may begin moving outward, only to discover that it was never moving quite fast enough. For material to escape permanently from a gravitational field, it must have enough energy to avoid being pulled back. In simple terms, it must reach the required escape velocity for its position within the star. During a powerful supernova, much of the stellar mantle and envelope can be accelerated beyond that threshold and thrown into interstellar space. But a weaker or highly uneven explosion may leave some material moving outward with too little energy to escape. It rises away from the center. It slows. Gravity gradually wins. And the material falls back. This process is known as fallback. Fallback provides one of the most important routes by which a star can appear to produce a successful supernova and still end up creating a black hole. The returning material does not all come back at once. Some matter remains only weakly displaced from the central remnant and can return within seconds. Other layers may travel much farther through the expanding star before gravity reverses their motion. Those regions can take minutes, hours, or sometimes longer to return. The exact timing depends on where the material began, how much energy the explosion gave it, and how the gravitational field changes as the rest of the star expands. At the center, there may initially be a proto-neutron star. If the early explosion removed enough surrounding material, that object might have survived indefinitely as a neutron star. Fallback changes the calculation. Every portion of returning matter adds mass. Gas plunging toward the neutron star releases tremendous gravitational energy as it approaches the surface. Some of that material may be heated intensely. Some may briefly form circulating flows around the remnant. But if the matter is ultimately captured, the central object becomes heavier. At first, the neutron star can adjust. Its internal pressure increases as gravity becomes stronger. Neutron degeneracy pressure and nuclear interactions continue supporting it. But there is a maximum amount of mass those mechanisms can carry. If fallback pushes the neutron star beyond its maximum stable mass, equilibrium becomes impossible. The object collapses again. Its radius decreases rapidly, space-time becomes more strongly curved, and an event horizon forms. A black hole has been born. This is delayed black hole formation. It differs from prompt black hole formation, in which the central remnant becomes too massive to survive during the initial collapse itself. In prompt formation, there may be little or no prolonged neutron star phase. In delayed formation, the star can briefly produce a genuine neutron star or proto-neutron star before later destroying that state by adding more mass. The delay does not need to be especially long by human standards. A neutron star that survives for seconds before collapsing has still existed as a distinct physical state during that interval. In other circumstances, the transition can take considerably longer if fallback occurs more gradually. The amount of fallback is closely connected to the strength of the explosion. A powerful explosion gives more of the surrounding material enough kinetic energy to escape. A weaker explosion leaves more matter gravitationally bound. This means that two collapsing stars with similar cores can potentially leave very different remnants if one explosion succeeds more energetically than the other. A strong explosion may eject enough mass to leave behind a neutron star. A weaker one may initially launch material outward, but later return so much of it that the central object becomes a black hole. This also corrects a common assumption about black hole birth. A black hole does not necessarily form only when a star disappears without producing a visible supernova. A bright stellar explosion and black hole formation can occur in the same event. The outer star can be expelled while the central remnant continues gaining enough mass to collapse. An astronomer watching from a distant galaxy might therefore see a supernova brighten dramatically without immediately knowing that the object left at its centre has become a black hole. Fallback can also change the final mass of that black hole. Suppose the central remnant crosses the neutron star limit and forms a relatively low mass black hole. The process does not necessarily stop there. Additional fallback material can continue crossing the event horizon. The black hole grows, a remnant that began near the lower end of the stellar black hole mass range may therefore accumulate several more solar masses from the debris of its own progenitor. How much it grows depends on how much material remains bound to the system. Fallback may also influence the black hole's motion. Supernovae are often asymmetric. If more material is ejected in one direction than another, the compact remnant can receive a recoil. Returning matter can alter that momentum again. Fallback is not necessarily distributed evenly, so material arriving from different directions can slightly change the remnant's motion through space. Angular momentum introduces another important effect. If returning gas carries substantial angular momentum, it cannot simply fall straight toward the black hole. Instead, it can begin orbiting. Material with enough angular momentum forms an accretion disk around the newly created black hole. Inside that disk, gas moves at enormous speeds and is heated as angular momentum is redistributed outward and matter gradually spirals inward. In especially rapidly rotating massive stars, this kind of black hole and disk system is central to the collapsar model. In a collapsar, the core of a massive star forms a black hole while rapidly rotating material around it forms a dense accretion disk. Energy released near the black hole can help drive narrow relativistic jets outward along the rotation axis. If one of those jets successfully punches through the surrounding star, it may produce a long-duration gamma-ray burst. These are among the most energetic electromagnetic events observed in the universe. Not every black hole formed through fallback produces a gamma-ray burst. Far from it. The star must have the right combination of mass, rotation, structure, and angular momentum, and the emerging jet must successfully escape through the surrounding stellar material. The collapsar pathway is therefore a specialized form of massive stellar collapse rather than the normal outcome of every fallback event. Predicting fallback remains difficult because many details matter simultaneously. The energy of the explosion is crucial. So is its asymmetry. The density structure of the star before collapse determines how tightly different layers are bound. Rotation changes the trajectories of returning material. Stellar winds may already have removed much of the envelope. A binary companion can strip material, transfer mass, or disturb the star before the collapse even begins. Small differences in these properties can substantially change how much matter escapes and how much eventually comes back. Fallback therefore occupies a useful middle ground between two cleaner pictures of stellar death. At one extreme, a successful supernova ejects enough material that the central neutron star remains safely below its maximum mass. At the other, the explosion fails badly, and the centre proceeds rapidly toward black hole formation, while much of the surrounding star continues inward. Fallback lies between them. The star does explode, material does move outward, a neutron star may genuinely form. But gravity has not quite finished. Some of the apparently escaping matter turns around and returns to the place from which it came. Piece by piece, the remnant grows heavier, and eventually enough of the star can come home to change the ending completely. Not every massive star manages to produce a successful supernova. Sometimes the collapsing core forms a shock, the shock stalls, and the processes that might have revived it simply do not provide enough energy soon enough. Matter keeps falling inward. The outer star remains gravitationally bound, and instead of producing the brilliant explosion usually associated with the death of a massive star, the event can proceed much more quietly toward black hole formation. This is generally described as a failed supernova. The name can be slightly misleading, because something enormously dramatic has still happened. The stellar core has collapsed. Nuclear density has been reached. Neutrinos have been produced in extraordinary quantities. The central object may briefly resemble a proto-neutron star. What has failed is the attempt to eject most of the star. After core bounce, the outward moving shock loses energy and stalls. In a successful explosion, neutrino heating, convection, turbulence, and other effects eventually help the shock expand again. In a failed supernova, that recovery is not strong enough. Material from the surrounding star continues raining through the stalled shock and onto the proto-neutron star. The central object grows heavier. If accretion continues rapidly enough, the proto-neutron star crosses its maximum stable mass. At that point, even the pressure of ultra-dense neutron-rich matter cannot maintain equilibrium. Collapse begins again. An event horizon forms, and within seconds of the original core collapse, the central object can become a black hole. This is one form of what astronomers often call direct collapse. The phrase does not necessarily mean that the star moves instantly from an ordinary stellar core to a black hole without passing through any intermediate state. A proto-neutron star may exist briefly. A shock may still form. Neutrinos may still escape. The star may undergo significant internal motion. Direct collapse is better understood as a broad description for black hole formation in which relatively little of the surrounding stellar material is successfully expelled by an ordinary supernova explosion. Even an apparently quiet collapse may not be completely invisible. One subtle effect comes from neutrinos. As the central core collapses and forms a proto-neutron star, vast amounts of energy escape in neutrinos. Because energy contributes to gravitational mass, the central object becomes slightly less massive gravitationally as this neutrino energy leaves. That small reduction can matter to the loosely bound outer layers of a very extended star. A red supergiant, for example, may possess a diffuse hydrogen envelope extending hundreds of millions of kilometers from the center. If the gravitational pull from the core weakens slightly and suddenly, some of that outer material may respond by moving outward. The result could be a faint and relatively slow ejection rather than a normal bright supernova. So even a failed supernova does not necessarily mean that every piece of the star falls silently into the black hole. There can be weak shocks, modest outflows, neutrino emission, and disturbances moving through the outer envelope. Astronomers have tried to find these events in an unusual way. Instead of searching only for stars that suddenly become brighter, they can repeatedly photograph large populations of massive stars and look for one that simply disappears. The idea is wonderfully straightforward. If a massive luminous star is visible in one set of observations, then later vanishes without producing the expected bright supernova, it may have collapsed into a black hole. One of the most discussed candidates is the object known as N6946 Black Hole 1. It was associated with a massive star in the galaxy N6946 that appeared to brighten temporarily and then faded dramatically. The behavior attracted attention because it seemed compatible with the possibility of a failed supernova followed by black hole formation. However, the interpretation remains uncertain. Dust can obscure stars, massive stars can undergo complicated eruptions. The surviving infrared emission from the region has allowed different explanations to remain possible. So N6946 Black Hole 1 is an intriguing candidate rather than a perfectly confirmed case of a star being watched as it quietly became a black hole. Another clue comes from binary stars. In the Large Magellanic Cloud, astronomers studying the Tarantula Nebula identified a stellar mass black hole in a system catalogued as 243 in the Very Large Telescope Fibra Large Array Multi-Element Spectrograph Tarantula Survey. The work involved a team led through observations associated with the European Southern Observatory. The black hole is considered dormant because it is not currently producing the powerful X-ray emission normally associated with a bright accretion disk. Instead, its presence was inferred from the motion of its visible companion star. The shape of the orbit is particularly interesting. The binary remains close to circular. If the black hole had formed in a violently asymmetric supernova that expelled a large amount of matter, the orbit might have been strongly disturbed and the remnant might have received a substantial natal kick. The relatively undisturbed system instead suggests that the black hole may have formed with little mass ejection and a comparatively small kick. That does not provide a perfect movie of the original collapse, but it gives astronomers evidence about what that collapse may have been like. Systems like this are difficult to discover precisely because they are quiet. A black hole does not glow by itself in ordinary light. If it is not consuming much material from a companion, there may be no hot accretion disk producing strong X-rays. If it is not currently merging with another compact object, there is no powerful gravitational wave signal announcing its presence. An isolated black hole formed through quiet collapse could therefore spend most of its existence almost completely dark. Its gravity remains, but unless that gravity noticeably affects something astronomers can see, the object can hide remarkably well. Quiet collapse also has an important effect on black hole mass. A powerful supernova can eject a substantial fraction of the original star. A weak or failed explosion leaves more material gravitationally bound. More of that matter can continue inward and eventually join the black hole. Direct collapse therefore provides a natural route to relatively heavy stellar mass black holes. This becomes especially important for massive stars that have already retained large amounts of material because of weak stellar winds or low metallicity. The less material lost before collapse, and the less material ejected during collapse, the more mass can remain in the final black hole. None of this means that failed supernovae are astrophysically uneventful. Space-time changes as the core contracts. Neutrinos stream outward. A proto-neutron star may briefly exist, weak shocks may move through the envelope, some material may escape, other material can fall inward. The event can be extraordinarily energetic at the centre, while remaining surprisingly unimpressive in visible light. That possibility may also help explain an observational puzzle. Astronomers have identified many red supergiants that appear massive enough to undergo core collapse, yet the highest mass members of this population seem less common among the directly detected progenitors of ordinary supernovae than might be expected. One possibility is that at least some of these stars do not produce conventional bright explosions. They may instead collapse largely into black holes. If so, the birth of a black hole can sometimes be marked not by one of the brightest explosions in the universe, but by something far stranger. A massive star simply stops being there. It is tempting to imagine that nature keeps a simple rulebook for making black holes. Below one particular stellar mass, perhaps a neutron star. Above it, a black hole. That would certainly make things easier. But the more closely astronomers study massive stars, the less realistic that picture becomes. Initial mass matters enormously, but it does not act alone. A star changes throughout its life. It loses matter, mixes material internally, interacts with magnetic fields, sometimes exchanges mass with a companion, and builds a core whose structure can be surprisingly different from another star that began with almost the same mass. So when astronomers say that stars born above roughly 20 solar masses become increasingly likely to form black holes, that is a useful broad guide. It is not a universal boundary. One reason is metallicity. In astronomy, metallicity describes the abundance of elements heavier than hydrogen and helium. Stars with higher metallicity generally drive stronger stellar winds. Those winds are powered partly through interactions between radiation and heavier elements in the stellar atmosphere. Over millions of years, they can remove enormous amounts of material. A very massive star born in a metal-rich environment may therefore lose much of its outer envelope before its core ever collapses. A similar star born with much lower metallicity can retain far more mass. That changes both the mass of the final core and the amount of material available to fall inward during the collapse. The cosmic environment therefore matters. The earliest generations of stars formed when the universe contained almost nothing except hydrogen, helium, and tiny amounts of a few other light elements. These first stars had extremely low metallicity. Because their winds were probably weaker than those of many massive stars today, some may have retained far more of their birth mass until death. That makes early cosmic environments especially interesting when considering the formation of heavy stellar black holes. A star born in the modern Milky Way and a star born in the young universe might begin with similar masses but end with very different remnants. Rotation adds another complication. Stars do not simply sit still while they evolve. Many massive stars rotate rapidly. Rotation can mix material between different layers, carrying fresh hydrogen into regions where fusion is occurring and transporting newly created elements elsewhere. That mixing can change how large the helium core eventually becomes. Rotation can also affect mass loss and alter the amount of angular momentum preserved in the core. If much of that angular momentum survives until collapse, it can influence the spin of the resulting neutron star or black hole. Magnetic fields can modify this process further. Fields threading the stellar interior can transport angular momentum between the core and the surrounding layers. A rapidly rotating core can therefore be slowed as angular momentum is transferred outward. Alternatively, different evolutionary histories can preserve more rotation. The final spin of a compact remnant is not simply a scaled-down version of the rotation the original star once had. The interior has spent millions of years redistributing angular momentum before the collapse occurs. Then there are binary stars. For massive stars, binarity is not a minor complication. A large fraction of them interact with companions during their lives. One star can expand until material flows onto the other. A companion can strip away the hydrogen envelope entirely. Mass can move in the opposite direction and make a star heavier. Transferred material can also spin a star up. All of this can change the size of the eventual core and the way the star approaches collapse. The interaction can become even more dramatic during common envelope evolution. In this situation, one star expands so far that its companion becomes engulfed inside the same extended envelope. The two stellar cores then orbit within that shared gas. Drag removes orbital energy and angular momentum, causing the stars to spiral closer together. The envelope may eventually be expelled, or the two stars may merge. Either outcome can produce a pre-collapse object that looks very different from a star evolving alone. A stellar merger can create an unusually massive or rapidly rotating star. A stripped binary star may reach collapse with almost no hydrogen envelope at all. So even before the central core begins falling inward, the star may already have experienced a remarkably complicated life. The internal structure at the moment of collapse then becomes especially important. One useful concept is core compactness. Compactness describes, in broad terms, how much mass is concentrated within a relatively small radius inside the star. A highly compact core can feed material onto the proto-neutron star rapidly after collapse begins. That increases the rate at which the central object gains mass, and also makes the surrounding material more tightly gravitationally bound. The supernova shock then has a harder job. A less compact structure may give the shock a better opportunity to expand and eject the star. This is one reason original stellar mass alone does not reliably predict the outcome. Late nuclear burning can produce complicated internal structures. Carbon, neon, oxygen, and silicon burning do not always proceed in perfectly smooth layers. Burning shells can interact. Convection can mix material. The density profile of the core can change in ways that do not vary smoothly with the star's original mass. The result is what researchers sometimes describe as islands of explodability. Imagine arranging stars by their birth masses. The simplest expectation would be that low-mass core collapse stars explode successfully, followed by some single boundary, after which every more massive star forms a black hole. Detailed models often predict something less orderly. One initial mass may produce a successful explosion and leave a neutron star. A slightly heavier star may fail and form a black hole. Increase the initial mass again, and another model may explode successfully. The outcome can alternate, because the detailed structure of the core is changing in a complicated, non-monotonic way. Even the collapse itself is not perfectly smooth or symmetrical. Turbulent motion can already exist in the burning shells before the core gives way. Small differences in density and velocity can be carried into the collapse. Behind the stalled shock, convection and turbulence amplify asymmetries. These variations can influence whether a marginal shock is successfully revived. That does not mean black hole formation is simply random. The fundamental physics still determines what outcomes are possible. But when a star is close to the boundary between a successful and failed explosion, comparatively small structural differences can matter. This leaves us with a more realistic way of thinking about mass thresholds. A star born above roughly 20 solar masses is generally more likely to produce a black hole than one born just above the lower limit for core collapse. As birth mass rises, the cores can become larger, fallback can become more important, and failed explosions can become more likely. But that trend is statistical rather than absolute. Metallicity changes mass loss. Rotation changes mixing and angular momentum. Magnetic fields redistribute that rotation. Binary companions remove or add material. Common envelope evolution and stellar mergers can reconstruct the star almost completely, and the detailed compactness of the final core can determine whether the supernova shock succeeds. There is therefore no single birth mass at which nature suddenly changes its mind and begins producing black holes. The boundary is better imagined as an overlapping region of possibilities. Some stars in that region leave neutron stars. Others form black holes. The probability changes as the star becomes more massive, but the final answer depends on what the star has actually become by the time its core collapses. The original mass sets the stage. The entire life of the star decides how the final scene plays out. At very high stellar masses, the path from star to black hole becomes strange once again. It might seem reasonable to assume that if one star is more massive than another, it should simply produce a more massive black hole. For a while, that general tendency can hold. Then a new piece of physics intervenes. Inside an extremely massive star, particularly one that has retained a large helium core and formed in an environment with relatively low metallicity, the central temperature can become so high that energetic photons begin doing something unusual. They can transform into pairs of particles. One is an electron. The other is its antimatter counterpart, the positron. This is known as electron-positron pair production. Under less extreme conditions, radiation inside the star provides part of the outward pressure resisting gravity. In a very massive, extremely hot core, photons can carry enormous energies. When some of those photons create electron and positron pairs, part of the radiation energy is converted into the rest mass of these newly created particles. That matters because the pressure supplied by the radiation no longer responds to compression in quite the same way. The core becomes less able to resist gravity. It begins to contract. And because gravitational contraction heats the material, the temperature rises still further. Pair production therefore creates an instability. The hotter the core becomes, the more important the effect can become. The core contracts more strongly, temperature rises, nuclear reactions accelerate. For the right range of stellar core masses, the result can be extraordinarily violent. One possibility is known as pulsational pair instability. In this case, the contraction caused by pair production heats the core enough to trigger explosive nuclear burning, particularly involving oxygen. The energy released can temporarily reverse the collapse. The star expands violently and may eject an enormous amount of material, but the entire star is not necessarily destroyed. After the pulse, the surviving core can settle down again. Then it can contract once more. Another pulse may follow. Some stars can experience several of these violent episodes. Each pulse can throw away additional mass. The process may continue over a period ranging from relatively short intervals to much longer separations, depending on the stellar model and the strength of the pulses. Eventually, the remaining core can proceed toward ordinary core collapse and produce a black hole. But by then, the star may have lost a substantial amount of the material it once possessed. This creates an important limit on the mass of the final black hole. A star can begin with an enormous mass, yet pulsational pair instability can repeatedly strip material away before the final collapse. Instead of producing an increasingly heavy black hole, the star is forced to shed some of the very mass that would have entered it. At somewhat greater core masses, the outcome can become even more dramatic. The instability can trigger such powerful explosive oxygen burning that the energy released completely disrupts the star. This is known as a pair instability supernova. In that case, there is no surviving central remnant. No neutron star remains, no black hole forms. The star is simply destroyed. Its material expands outward into space, leaving no compact object behind. This makes pair instability fundamentally different from the ordinary core collapse events that produce neutron stars or black holes. The central question is no longer whether the supernova ejects enough matter to save a neutron star. The thermonuclear explosion can become powerful enough to unbind the entire star. The theoretical foundations of this idea developed through work by several 20th century researchers. William Fowler and Fred Hoyle investigated the behavior of pair production and nuclear burning in very massive stellar interiors. Later calculations by Zalman Barkat, Gideon Rakavi, and Jura Shaviv helped establish how electron-positron pair production could destabilize massive stars and lead to explosive outcomes. Their work revealed something counterintuitive. Above certain masses, making a star heavier does not necessarily make the final black hole heavier. For a particular range of core masses, it may prevent a black hole from forming at all. This is one reason astronomers expect what is often called an upper black hole mass gap. The rough idea is that ordinary stellar evolution may struggle to produce black holes within a broad region somewhere around 60 to 130 solar masses. Those numbers should not be treated as perfectly sharp boundaries. The precise edges depend on the details of the stellar models. Nuclear reaction rates matter. Metallicity matters. Rotation matters. Mass loss matters. The internal structure of the star matters. Different calculations can therefore move the expected boundaries significantly. There is also an important distinction between the mass of the original star and the mass of its helium core. Pair instability is driven mainly by conditions inside the hot central core. A star born with an enormous total mass may lose much of its outer material before reaching this stage. Its final helium core may therefore be much lighter than the birth mass might suggest. Two stars with similar original masses can again end up in different places because one loses far more material than the other. So saying that every star above some particular initial mass undergoes pair instability would be misleading. The core mass is the more relevant quantity. At still greater masses, another change may occur. A sufficiently massive core can become so strongly bound that even explosive nuclear burning may no longer destroy it completely. Photodisintegration becomes especially important. Extremely energetic photons break heavy nuclei apart. That process absorbs energy instead of releasing it. If enough energy is consumed in this way, the collapse can continue despite the enormous temperatures involved. The result may be the formation of a black hole above the predicted pair instability gap. So the rough pattern becomes surprisingly complicated. Below the pair instability regime, massive stars can collapse and produce black holes. Move into the pulsational regime, and repeated eruptions can strip mass away before black hole formation. Move farther upward, and a full pair instability supernova may destroy the star completely. Move to still more extreme cores, and collapse may once again become possible. Nature has inserted a missing region into what might otherwise have been a smooth sequence of black hole masses. Observations have made this especially interesting. Astronomers have detected black holes with masses that appear to reach into regions where ordinary single-star evolution may have difficulty producing them. That does not immediately mean pair instability theory is wrong. There are other ways to create a black hole in the apparent mass gap. Two smaller black holes can merge. The resulting object is heavier than either of its parents. That merger product can later merge again. In dense stellar environments, this kind of repeated or hierarchical merger may build black holes that individual stars would struggle to create directly. Unusual stellar evolution could also shift the expected limits, so could uncertainties in nuclear physics and mass loss. The mass gap is therefore not expected to be an absolutely empty forbidden zone. It is better understood as a region where direct production from ordinary stellar collapse may be strongly suppressed. This is another reminder that black hole mass does not simply track stellar mass in a straight line. A heavier star can lose more material. A still heavier one can pulse violently. A heavier one again may completely destroy itself. And only at even greater extremes may collapse return. Pair instability places an interruption in the ordinary stellar route to black hole formation. It creates a natural barrier between many of the heaviest black holes formed directly from individual stars and still larger objects that may require mergers or more exotic evolutionary histories. Adding more mass does not always make gravity's victory easier. Sometimes it gives the star enough energy to destroy itself before a black hole can be born. Once a collapsing stellar remnant becomes too massive for any known form of pressure to support it, there is no longer a stable neutron star configuration available. Gravity continues pulling the matter inward. The radius shrinks, the density rises, and general relativity predicts that eventually the collapsing material becomes compact enough for something fundamentally new to appear. An event horizon forms. This is the moment the object becomes a black hole. It is important to be precise about what an event horizon actually is, because it is often described as though it were a physical surface. It is not. There is no solid wall surrounding a black hole. There is no shell of material marking the boundary. The event horizon is a boundary in space-time itself. Outside that boundary, there are paths that light and matter can follow which lead away from the black hole. Inside it, every future-directed path leads farther inward. Even light cannot choose a route that carries it back out. This is not because light suddenly slows down or because some invisible surface grabs it. Locally, light still moves at the speed of light. The difference is that space-time has become curved so strongly that all possible future directions point deeper into the black hole. The earliest mathematical description of this kind of space-time came from Carl Schwarzschild. In 1916, only months after Albert Einstein published the final form of the general theory of relativity, Schwarzschild found an exact solution to Einstein's field equations for the space-time outside an ideal spherical, non-rotating mass. That solution revealed a characteristic radius associated with a sufficiently compact object. Today it is known as the Schwarzschild radius. For every solar mass contained in a non-rotating black hole, the Schwarzschild radius is approximately 3 kilometers. So a black hole containing 10 times the mass of the Sun would have an event horizon with a radius of roughly 30 kilometers. In spoken form, the relationship is pleasantly simple. The horizon radius is approximately 3 kilometers multiplied by the black hole's mass measured in solar masses. This gives a useful sense of how extreme black hole formation really is. The Sun contains one solar mass, but its present radius is almost 700,000 kilometers. To become a black hole without gaining any additional mass, the Sun would somehow have to be compressed until that mass fitted inside a radius of only about 3 kilometers. The Sun will never do this naturally. It is nowhere near massive enough to undergo the required kind of collapse. But a massive stellar remnant can. A 10 solar mass remnant need only contract inside a region around 30 kilometers in radius before the event horizon appears. That size is comparable to the scale already being approached during the collapse of extremely compact stellar cores. The newly formed black hole is also unlikely to be perfectly non-rotating. Real stars rotate. Their cores rotate. Binary interactions can spin stars up. Fallback material can deliver additional angular momentum. So a more realistic description of an astrophysical black hole usually involves rotation. In 1963, Roy Kerr found the exact solution describing an ideal rotating black hole. A rotating black hole is now often called a Kerr black hole. The amount of spin retained by the newborn black hole depends on the entire previous history of the star. Magnetic torques can transport angular momentum out of the core before collapse. Stellar winds can remove rotating material. A binary companion can either increase or decrease the rotation. Fallback can deliver fresh angular momentum after the central black hole has already formed. The black hole's spin is therefore not simply the original star's rotation squeezed down to a smaller size. Much of the star's angular momentum may already have been redistributed or lost. As collapse proceeds beyond the formation of the event horizon, classical general relativity predicts that matter continues inward. This is where the idea of a singularity enters the discussion. A singularity should not be confused with the event horizon. The horizon is a boundary that can be described using well-established general relativity. The singularity is associated with what the classical equations predict happens deeper inside, when gravitational collapse continues without limit. In simplified black hole solutions, quantities such as spacetime curvature can become formally infinite, but saying that astronomers have observed an infinitely dense point inside a black hole would be inaccurate. They have not. No signal can travel outward from inside the event horizon to show us directly what happens there. And most physicists expect that a complete theory of quantum gravity would be needed to describe the deepest interior properly. General relativity is extraordinarily successful, but it is a classical theory. At sufficiently extreme densities and curvatures, quantum effects are expected to become important. Roger Penrose helped establish just how difficult it is to avoid this problem within classical general relativity. In the 1960s, Penrose developed a singularity theorem showing that under broad physical conditions, once gravitational collapse creates a trapped surface, spacetime becomes geodesically incomplete. In simple terms, the classical theory predicts that certain paths through spacetime cannot be continued indefinitely. The result does not tell us exactly what quantum physics replaces the classical singularity with. It tells us that ordinary classical spacetime cannot remain completely well behaved all the way inward. For the formation of the black hole itself, however, the event horizon is the crucial feature, and the horizon does not necessarily appear at its final size. A black hole can form while additional stellar material is still falling inward. The central region may first cross the threshold required to create a trapped surface. After that, more matter from the surrounding star can cross the horizon. Fallback material can arrive later. Gas from a companion star may be accreted over millions or billions of years. The horizon grows as the mass of the black hole grows, so the first black hole created during stellar collapse may be lighter than the final object astronomers observe much later. A black hole produced from a collapsing star can therefore continue evolving long after the instant of its birth. Once it settles into an isolated state, classical general relativity describes an astrophysical black hole using only a small number of externally measurable properties. Its mass matters. Its angular momentum, or spin, matters. Electric charge is also allowed in the mathematical description. In practice, large astrophysical black holes are expected to carry very little lasting net electric charge because surrounding plasma contains both positive and negative charges. If a black hole became strongly charged, it would tend to attract opposite charge from its surroundings and neutralize itself. So mass and spin are usually the dominant properties astronomers care about. This makes the contrast with a neutron star especially clear. A neutron star has a physical surface. Matter falling onto it can strike that surface. The impact can heat material, release radiation, and produce observable bursts or hot regions. The neutron star can support matter above its center because its internal pressure balances gravity. A black hole has crossed beyond that possibility. Its event horizon is not something that pushes back against incoming material. Matter crossing the horizon does not hit a hidden crust. It simply continues along paths that remain inside, and this clarifies what it really means for a star to become a black hole. The star is not swallowed by some separate black object waiting in the middle. Nothing arrives from elsewhere. The black hole is created by the star's own collapse. The stellar core becomes so compact that its gravity curves space-time into a region from which no future path leads back out. An event horizon forms around the collapsing matter. The star has created the boundary through its own mass. For millions of years, gravity was balanced by pressure. Then, electron degeneracy failed. Neutron-rich matter provided one final stable possibility. And when even that could no longer hold, the collapse changed the structure of space-time itself. The star did not fall into a black hole. The star became one. A black hole can be one of the most difficult objects in the universe to observe directly. The reason is almost contained in the name. A black hole does not have a glowing surface. Its event horizon does not reflect ordinary light, and a quiet black hole surrounded by almost nothing can remain almost completely dark. If there is no nearby gas to heat up, no companion star to disturb, and no merger taking place, there may be very little for a telescope to see. The black hole is still there. Its gravity still affects the space around it. But detecting that influence can be surprisingly difficult. This is one reason binary star systems are so important. Many massive stars form in pairs or in larger multiple systems. That means a star destined to become a black hole may already have a companion long before the collapse begins. If that companion survives the explosion or direct collapse, it can later provide astronomers with a way to detect the hidden remnant. One of the clearest examples comes from X-ray binaries. In these systems, a black hole orbits a normal star closely enough to pull gas away from it. The stolen gas does not usually fall straight into the black hole. Because the material carries angular momentum, it begins orbiting instead. It spreads into a flattened structure known as an accretion disk. Gas within that disk moves at enormous speeds. Different regions orbit at different rates, and turbulence, magnetic stresses, compression and friction-like processes convert some of the orbital energy into heat. The inner parts of the disk can reach temperatures of millions of degrees. At those temperatures, the material emits strongly in X-rays, so the black hole itself remains dark, but the matter surrounding it can become extremely bright. This is one of the great ironies of black hole astronomy. Some of the most dramatic radiation associated with a black hole is produced precisely because matter has not crossed the event horizon yet. The glow comes from the final stages of the journey outside it. This also helps correct one of the most persistent misconceptions about black holes. They are not cosmic vacuum cleaners endlessly sucking in everything nearby. At a safe distance, the gravity of a black hole behaves mainly according to its mass, just as the gravity of any other object does. If the Sun could somehow be replaced instantly by a black hole with exactly the same mass, Earth would not suddenly spiral inward. Its orbit would remain almost the same. The obvious problem would be the disappearance of sunlight, which would be unpleasant for several reasons. A black hole captures matter efficiently only when that matter passes close enough and loses enough orbital energy to fall inward. Companion stars therefore become especially useful because their motion reveals what cannot be seen directly. One famous case is Cygnus X1. This system became the first widely accepted strong stellar black hole candidate. Astronomers observed a luminous massive star orbiting something that could not be seen directly. Work by Louise Webster, Paul Murdin, Tom Bolton, and others showed that the visible star was moving around an unseen companion with substantial mass. That immediately raised an important question. How massive was the invisible object? Astronomers can estimate this using dynamical measurements. By tracking the visible star's orbital period, speed, and motion, they can calculate how much gravitational influence the unseen companion must be exerting. If the inferred mass is comfortably above the plausible maximum for a neutron star, a black hole becomes the most convincing explanation. This is one of the most powerful methods in compact object astronomy. You do not need to see the black hole itself. You watch what its gravity does to something you can see. Cygnus X1 also emits strong X-rays because material from the visible companion is being drawn toward the black hole and heated in the process. That makes it comparatively easy to notice. But not every stellar black hole is so cooperative. Some are dormant. A dormant black hole is not necessarily completely inactive, but it is not currently accreting enough material to produce a bright X-ray source. The black hole in the binary system VFT S243 is an example. Its presence was inferred largely through the motion of its luminous companion rather than through a powerful glowing accretion disk. The system is especially valuable because it demonstrates that black holes can hide in ordinary-looking binaries. There may be many more like it. An isolated black hole presents an even greater challenge. With no companion star nearby, astronomers may have almost nothing obvious to track. One possible method is gravitational microlensing. If a compact object passes almost directly between Earth and a more distant background star, its gravity bends the light from that star. The background source can temporarily appear brighter. The apparent position of the star can also shift slightly. A black hole does not need to emit any light for this to happen. Its mass is enough. By studying the duration and shape of the lensing event, and in some cases the tiny positional shift of the background star, astronomers can estimate the mass of the unseen lens. This creates one of the few possible routes to finding isolated stellar remnants wandering quietly through the galaxy. But every detection method introduces selection effects. Astronomers naturally find the black holes that announce themselves most clearly. A black hole feeding rapidly from a companion produces bright X-rays and may be discovered relatively easily. A black hole in a binary can reveal itself through the motion of the visible star. A merging pair can produce gravitational waves. A quiet, isolated black hole might do almost nothing noticeable for millions or billions of years. The observed population is therefore not necessarily representative of the true population. The Milky Way is expected to contain millions of stellar mass black holes produced by generations of massive stars. Only a tiny fraction have been individually identified. Most may simply be drifting through the galaxy without doing anything dramatic enough to attract attention. This makes each well-studied system valuable for more than simply confirming that a black hole exists. The orbit of a surviving companion can preserve clues about the collapse that created it. A strongly eccentric orbit may suggest substantial mass loss or a natal kick during formation. A nearly circular system can point toward a quieter collapse with relatively little disturbance. The black hole's mass can reveal how much of the original star was retained. Its spin may preserve information about rotation, binary interaction, and later accretion. The surrounding disk can show how matter behaves in the strong gravitational field outside the event horizon. So although the black hole itself gives us almost no ordinary light, it is not completely hidden. It leaves fingerprints on everything around it. A companion star moves differently. Gas heats to millions of degrees. Background starlight bends. Orbits shift. Matter spirals inward. The black hole remains dark at the center of all of this, but gravity makes sure that its presence is rarely entirely silent. When two black holes orbit one another, their motion is not perfectly silent. They disturb space-time itself. Those disturbances spread outward as gravitational waves, carrying energy and angular momentum away from the system. As energy leaves, the orbit gradually shrinks. The black holes move closer together, circle one another more quickly, and produce stronger gravitational waves. Eventually, the slow spiral becomes a rapid plunge. The two horizons merge. A larger black hole remains. Albert Einstein predicted gravitational waves in the early 20th century as a consequence of the general theory of relativity. They are not sound waves moving through air or any other material. They are propagating distortions in space-time itself. For decades, gravitational waves remained extraordinarily difficult to detect, because even violent cosmic events stretch and squeeze space by extremely tiny amounts by the time the signal reaches Earth. That changed in 2015. The Laser Interferometer Gravitational Wave Observatory directly detected a signal produced by two merging stellar mass black holes. The event became known as Gravitational Wave 150914 because it reached Earth on September 14, 2015. The achievement rested on decades of work involving researchers including Rainer Weiss, Kip Thorne, Ronald Drever, and a large international community of scientists and engineers who developed the detectors, optical systems, vibration isolation, data analysis, and theoretical models needed to identify such a faint signal. The two black holes involved were unexpectedly heavy by the standards of many previously known stellar black holes. One had a mass of roughly 36 suns. The other contained around 29 solar masses. They merged to produce a black hole of approximately 62 solar masses. Those numbers do not quite add up. 36 plus 29 is about 65. The missing several solar masses were not lost in the ordinary sense. Their equivalent energy was carried away as gravitational waves. For a fraction of a second, the merger released an astonishing amount of power through the changing geometry of space-time. The signal itself had a characteristic rising pattern often called a chirp. As the black holes moved closer together, their orbital speed increased. The gravitational waves rose in frequency. Their amplitude also increased as the merger approached. That changing pattern contains information about the system. By comparing the observed waveform with predictions from general relativity, researchers can estimate the masses of the black holes, their spins, their distance, and aspects of their orbital motion. The addition of the Virgo detector in Europe, followed later by the Kamioka gravitational wave detector in Japan, expanded the network. Multiple detectors can confirm that a signal is genuinely astrophysical and help determine which part of the sky it came from. But gravitational waves offer something even more valuable than individual spectacular events. They reveal populations. Each detected merger adds another pair of black hole masses and spins to the astronomical record. Collect enough of them, and those measurements become a form of stellar archaeology. The mass of a black hole carries clues about the star that created it. Heavy black holes may point toward low metallicity environments where massive stars lost less material through stellar winds. The spin can contain information about the star's rotation, binary interaction, and later accretion. The motion of the binary can reveal clues about whether the black holes received strong natal kicks when they formed. Researchers can therefore compare the observed population with models of stellar evolution, supernova explosions, failed supernovae, fallback, and binary mass transfer. The emerging distribution has already made the boundary between neutron stars and black holes look less tidy. Some gravitational wave events contain compact objects in the possible lower mass gap, between the heaviest confidently known neutron stars and the lightest familiar black holes. In certain cases, the measurements alone cannot tell us with complete confidence which kind of compact object was present. At the opposite end of the mass range, gravitational waves have revealed black holes that are unexpectedly heavy. One particularly important event, gravitational wave 1905-21, involved two black holes with masses of roughly 85 and 66 solar masses. Their merger produced a remnant of around 142 solar masses. That placed the final object in the intermediate mass range. The heavier member of the original pair was also interesting, because its estimated mass lay in the region where pair instability may make direct formation from an ordinary single star difficult. One possible explanation is hierarchical merging. A black hole formed from an earlier stellar collapse can merge with another black hole. The remnant is heavier. If that remnant remains inside a dense stellar environment, such as a massive star cluster, it may later encounter another black hole and merge again. Repeated mergers can therefore build objects whose masses individual stars struggle to produce directly. This does not mean gravitational waves allow astronomers to reconstruct every progenitor star in perfect detail. Usually, the original stars are long gone by the time the black holes merge. The detectors measure the compact remnants, not the entire lives that produced them. Researchers must therefore compare populations statistically with models of stellar evolution. Even so, every merger preserves part of the history. A black hole's mass reflects how much of its progenitor star survived winds, explosions, and fallback. Its spin may preserve traces of stellar rotation and binary interaction. Its orbit can record the effects of earlier collapse and natal kicks. And an unusually heavy black hole may reveal that another merger happened before the one we detected. A gravitational wave signal lasts only moments in our detectors, but hidden inside that brief ripple is an imperfect record of events that may have begun millions or billions of years earlier, when two ordinary massive stars were still shining. Black holes are often grouped into classes, but the divisions are based mainly on mass rather than on fundamentally different kinds of objects. A black hole with 10 times the mass of the Sun and one with 10 billion times the Sun's mass both possess an event horizon. Both are described by the same underlying framework of general relativity. Both can rotate. Both can accrete matter. Both can merge with other black holes. What changes most dramatically is scale. The boundaries between the different mass classes are not perfectly fixed, and they may shift as new observations reveal objects in regions that once seemed sparsely populated. The smallest well-established astrophysical category is the stellar mass black hole. These are the objects produced most directly by the deaths of massive stars. A typical stellar mass black hole may contain anywhere from a few times the mass of the Sun to several tens of solar masses. Some can be heavier. Stars forming in environments with low metallicity can lose less material through stellar winds, allowing larger cores to survive until collapse. Mergers can then create still heavier black holes that may no longer fit comfortably inside the simplest idea of a stellar remnant. It is also worth remembering that the mass of the original star and the mass of the final black hole are not the same thing. A star might begin its life with 30, 40, or considerably more solar masses. During its lifetime, powerful winds can remove large quantities of material. A binary companion can strip away the outer layers. The final explosion may eject more matter. Fallback can then return some of it. By the time the black hole settles into its final mass, only part of the original star may actually have entered the event horizon. The black hole is therefore the remnant of the star, not simply the entire original star compressed intact. Above the stellar mass range lies a much less completely understood population, known as intermediate mass black holes. Broadly speaking, these objects are expected to contain hundreds, thousands, or perhaps hundreds of thousands of solar masses. They occupy the enormous region between ordinary stellar remnants and the supermassive black holes found in galactic centers. For many years, this intermediate range was sometimes described as the missing link in black hole astronomy. Evidence for individual candidates has accumulated, but the population is still far less clearly mapped than either stellar mass or supermassive black holes. Several formation routes may be possible. In dense star clusters, stellar mass black holes can sink toward the center and interact repeatedly. Two may merge. The remnant can later merge again. Over time, repeated mergers can build a progressively heavier object. A black hole might also grow through sustained accretion if a sufficiently large supply of gas remains available. Another possibility involves the deaths of unusually massive stars in the early universe. Under the right conditions, these objects could leave remnants considerably heavier than the stellar black holes commonly produced today. Even more direct collapse scenarios involving large concentrations of gas may contribute at the upper end of the intermediate range. Gravitational waves have already shown that mergers can move black holes from one class into another. The event known as gravitational wave 190521 involved black holes of roughly 85 and 66 solar masses. Their merger produced a remnant of about 142 solar masses. That final object lies in the lower intermediate mass range, so an intermediate mass black hole does not necessarily need to begin life there. Two stellar-scale objects can combine and cross the classification boundary. At still greater masses lie supermassive black holes. These contain from hundreds of thousands of solar masses to billions of solar masses. They are found in the centers of most large galaxies. The Milky Way contains one called Sagittarius A star, with a mass of roughly 4 million suns. Other galaxies contain black holes hundreds or thousands of times heavier still. These objects cannot be explained by the ordinary collapse of a single modern star. Even the most massive conventional stars do not contain millions or billions of solar masses. A supermassive black hole must therefore either begin through a different formation process or grow enormously after its initial formation. One possibility starts with stellar remnants. The first generations of massive stars could have collapsed into black holes. Those objects would then act as seeds. Over hundreds of millions of years, they could gain mass by accreting gas and merging with other black holes. This is generally called a light seed scenario, because the starting black holes are relatively modest compared with the supermassive objects they eventually become. But observations of very massive black holes, surprisingly early in cosmic history, create a challenge. There may not always be enough time for an ordinary stellar remnant to grow from perhaps tens of solar masses to hundreds of millions or billions. That motivates heavy seed models. In these scenarios, very large concentrations of primordial gas collapse under gravity and form much heavier initial black holes. Some models involve the formation and collapse of supermassive stars. Others involve direct collapse of massive gas clouds while avoiding the ordinary fragmentation that would otherwise produce many smaller stars. The starting black hole might then contain thousands or tens of thousands of solar masses, providing a substantial head start. There is also a hypothetical class that is completely different in origin. Primordial black holes, if they exist, would not have formed from stars at all. They are proposed to have formed from unusually dense regions in the very early universe. Depending on the mechanism involved, their masses could span an enormous range. No primordial black hole population has yet been confirmed, so they remain hypothetical. Their importance here is mostly as a reminder that black hole classification and black hole formation are not the same thing. A black hole can begin in one mass class and later move into another. A stellar mass black hole can accrete material. It can merge with another stellar black hole. The resulting object may become an intermediate mass black hole. Repeated growth over cosmic time may contribute to much larger systems. The labels tell us what mass an object has now. They do not necessarily tell us every step in its history. This creates a broad hierarchy. At the lower end, individual massive stars can die and leave stellar black holes. Those remnants can interact and merge. Some may grow into intermediate mass objects. Black holes in the early universe may then serve as seeds for the supermassive objects that eventually dominate the centers of galaxies. Across this enormous range, from a few solar masses to billions, the defining feature remains the same. There is an event horizon. There is a region from which no future directed path leads back outward. What changes is how much mass has been gathered behind that boundary, and how the object arrived there. Only the stellar mass class can normally be traced directly to the collapse of a single conventional star. That is the scale on which the transformation from shining star to black hole occurs most naturally. The larger classes belong to a longer story. They are what can happen after black holes themselves are given enough time to grow. A star becomes a black hole only after a long sequence of changes has stripped away every other possible ending. Mass sets much of the initial course, but it does not decide the outcome alone. A massive star spends millions of years fusing hydrogen, then progressively heavier elements, while winds, rotation, magnetic fields, metallicity, and binary interaction reshape it along the way. Eventually, an iron-rich core forms. Fusion can no longer provide useful support, electron degeneracy pressure fails, and the center collapses in less than a second. Even then, gravity has not necessarily won. Matter stiffens near nuclear density. A proto-neutron star can form. Neutrinos flood outward. Turbulence and convection may help revive the stalled shock and produce a supernova. If the remnant stays below its maximum stable mass, a neutron star survives. If too much material remains, the outcome changes. A black hole may form promptly after a failed explosion through delayed collapse as fallback adds mass, or much later if an existing neutron star gains enough material to cross its final stability limit. Stars born above roughly 20 solar masses become increasingly likely to follow one of these routes, but there is no universal dividing line. Core structure, mass loss, rotation, metallicity, binary history, explosion strength, and fallback all matter. At still greater masses, pair instability can interrupt the pattern entirely, stripping a star repeatedly or even destroying it without leaving any compact remnant. The black holes that do survive can reveal themselves through companion stars, X-rays, gravitational lensing, neutrinos, disappearing stars, and gravitational waves. And although many questions remain, the basic transformation is clear. A star can shine for millions of years, balancing gravity almost perfectly. Then, in only seconds, that balance can disappear. What remains is not something separate from the star's life, but its final continuation under the same laws of physics. The light ends. Gravity remains.